Hi and welcome to this presentation. Today we're going to talk about a research project from 1achem, or the Institute of Frontiers Material at Deakin University. We're going to look into controlling corrosion of coronary artery stents. This is done through use of biocompatible ionic liquids. What is the purpose and rationale of this research? The purpose is to create a coating that protects magnesium-based coronary artery stents from corrosion. Why, you might be asking? Well, there is a need for biodegradable, more biocompatible stents, as current stents cause health and environmental problems. The purpose explained. So to create a coating that protects magnesium-based coronary artery stents from corrosion, that might be a little bit confusing when you first sort of listen to it. So I'll break it down for you so you can understand exactly what this purpose of the research is. Let's start with coronary artery stent. So coronary is related to the heart. Artery is a blood vessel or hose-like structure that carries blood away from the heart, and stent is a tube placed in the coronary arteries that keep the arteries open when they cannot stay open by themselves due to heart disease. Now let's look at corrosion. Corrosion is a gradual destruction of materials, usually metals, by chemical reactions with its environment. And we'll go to magnesium. A little bit about magnesium. It's a chemical element that is a metal found on Earth. It also can be found within our bodies and in the stars. It's used medicinally as laxatives and antacids. It's highly soluble in water and it's highly reactive. Now, magnesium has an excellent biocompatibility and biodegradability, which means it's capable of decomposing back into its natural elements. It's lightweight and has good mechanical properties. These properties include strength, ductility, hardness, plasticity, and resilience. So if we have a look at that purpose explained again, we are wanting to create a coating that protects against gradual destruction of a reactive metal that is used in heart-diseased vessels. So why would we make a stent out of magnesium? Well, the current stents being used have some long-term risks. They're made out of stainless steel, and as you can see on the right, they look very similar to the magnesium ones, but the problem with these stainless steel stents is that they cause chronic inflammation, in-stent restenosis, which is the narrowing of the blood vessels despite a stent being in place, which requires a second operation, and they're non-biodegradable. Now, if we have a quick look at those properties of the magnesium stent again, they were biocompatible, biodegradable, lightweight, with good mechanical problems. But the one thing wrong with magnesium is it will corrode. Hence the reason for this research, we need a coating. So why ionic liquids, and will it stick to the stent? How are we going to stop the corrosion of the magnesium? Well, the researchers have decided they want to use ionic liquid coating. An ionic liquid is a salt in a liquid state. Now, a salt is made up of an acid and a base, a positively charged molecule or a cation, and a negatively charged molecule or an anion. When looking at this ionic liquid, they need to make a coating that is A, compatible with conditions within a body, or biocompatible, B, has the ability to protect against corrosion, C, can be adhered to a magnesium-based stent, and D, can be tested to ensure that the above needs are met. So the overview of this method of research is the ionic liquid is pipetted onto the stent, it's clamped together, put into an oven, and this actually adheres the ionic liquid to the stent. Then it goes through the testing phase. Now let's look at this testing phase a little bit more. What we're doing is we're testing for surface characteristics and chemical identification. Those tests for surface characteristics include SEM, or scanning electron microscope. This produces images of a sample by scanning it with a focused beam of electrons. It gives information about the surface characteristics. IR, or infrared spectroscopy. This deals with the infrared region of the electromagnetic spectrum, longer wavelength and lower frequency than visible light. It's used to identify and study chemicals based on absorption spectroscopy. We've also got optical microscopy. This is a microscope that uses visible light and lenses to magnify images of small samples. And then we've also got the XPS, or X-ray photoelectron spectroscopy. This measures elemental compositions within a material. A spectra is obtained by irradiating a material with a beam of X-rays while measuring the kinetic energy and number of electrons that escape. It can specifically study any changes due to heating. We've also got tests for corrosion. We've got the immersion test. This measures the progress of corrosion damage obtained from the immersion duration within a corrosive environment. In this case, it's 37 degrees Celsius simulated body fluid. And we have the electrochemical test. This assesses the state of corrosion in a concrete or metal element. It's based on electrochemical theory that characterises corrosion damage and estimates the corrosion rates. Measures the oxidation or reduction reactions. Next, we'll move on to the overview of results. As you can see here on the right-hand picture there, or film, the ionic liquid film has adhered. You can see it just by this fine sort of little line. And also the bottom diagram is the IR spectra. This gives insight into the chemical reaction occurring during ionic liquid treatment. So as you can see, the upper image there, without the ionic liquid coating, you can see there that there is corrosion. The lower image with ionic liquid coating has suppressed corrosion. So we actually know from the research and from the results that ionic liquid coating can effectively suppress the corrosion. So what are some key chemical practices used by scientists to develop new knowledge and techniques? Well, speaking with Yafei, the research scientist on this project, enabled me to write some pointers on what scientists are actually doing out there to develop their new knowledge and their techniques. So Yafei thinks that you should deepen your understanding of knowledge, past and new. You can do this by having a continual passion for learning within a field. Example, reading recent studies, new discoveries, media reports. Have constant communication with peers, say sharing resources, and doing things like joining chemistry societies, clubs, online forums, and even competitions. You need to have a good attitude. Remain open-minded to all perspectives and ask for help when developing techniques. There is a creativity side to it. Developing new knowledge requires thinking creatively and innovatively. And get involved in areas other than chemistry to apply information to new contexts. And you need to find opportunities to practice new skills. So volunteer to assist at universities or schools. Know how to use equipment and technology through repetition, and find instructional videos online if you don't have the opportunity to operate equipment sort of hands-on. Moving on now from the research and sort of focusing more on the classroom, how does this relate to VCE students? Well, it does relate to Year 11, Unit 1, Chemical Fundamentals, Structure, Property and Reactions. In particular, the research relates to the area of study 2, materials, structure, properties and application of materials. The key knowledge that's covered is bonding to explain properties, metals, ionic compounds, including melting temperature, electrical conductivity, chemical reactivity, shape, polarity of bonds and intermolecular forces, and behaviour of surfaces and application of surface chemistry in nanotechnology. It can also be used, this research, as an introduction to redox reactions, let's say acids and bases, for Unit 2, Area of Study 1, and applications of spectroscopic techniques for Unit 3, Area of Study 1. How does this relate to Australian students? Well, the Australian curriculum, Chemistry, Unit 1, Chemical Fundamentals, Structure, Properties and Reactions. Now, it relates to science as a human endeavour. I'm not going to go through all of them, but if you'd like to stop the presentation, you can have a specific read through them. We've also got science understanding and science inquiry skills. Once again, feel free to stop the presentation and have a good look at those, because there are quite a few codes that it relates to. I'm also looked into the cross-curricular priorities that this research relates to. We do have Aboriginal and Torres Strait Islander histories and cultures. You can have a look at coronary health analysis, an alternative to stents through use of bush medicines and, their chemical properties. Asia and Australia's engagement with Asia. You can actually draw on Asian scientific research, collaborative projects, and Asian scientists, what they've contributed as well. And there's also sustainability. We can explore the importance of researching biodegradable stents and how stainless steel stents, which, as we've learned, are not biodegradable, how they impact the earth. We've also got the general capabilities covered in the research project. I could go through all of them, but it actually can cover every single one. You can once again pause and have a look there. And then we move on to our next part of the presentation. We're looking at the cutting edge science ideas on a macro, submicro and symbolic level. So what's macroscopic? That's what we see in the real world. Submicroscopic is underpinning chemistry concepts behind what we see, and the symbolic is how we represent these ideas. This research project can be sort of broken down into three areas or three sort of concepts, one being metals, two ionic bonding and three surfaces. And as we said, they always relate back to the curriculum. Let's look at the first concept from the macroscopic perspective. So we're looking at metals and their applications. So, relating that to the real world, we can say that the stainless steel and the magnesium stents are made of metals. They've got similarities, they're hard, high melting point density, etc. There's differences between them, which we've already covered, and the physical properties of metals can provide evidence of metal structure. That's all sort of the first step, the macro stage. If we move into the submicro, we're sort of looking more towards a structure of the metals. So sort of some concepts that we can introduce to students would be cations have lost an electron arranged in a three-dimensional lattice. Cations are surrounded by freely moving sea of mobile electrons. Electrons are delocalized. We can go into metallic bonding or electrostatic attraction, which holds the lattice together and prevents cations repulsing each other. The metal lattice also applies to all metals, and we can look at metal differences, which is dependent on the charge of the metal and the size of metal ions. There's also strength variance you can sort of touch on, which is smaller, highly charged ions equals greater electrostatic attraction to the sea, which produces obviously a stronger metallic bond. Still on the submicroscopic level, there's a lot more that we can cover, how the structure explains the properties. We've got a strong electrostatic attraction between cations and electrons. We can sort of relate things that like hardness, that it's difficult to separate. Considerable amount of heat energy needed to move ions from fixed positions equals a high melting point. We can relate high density to cations being packed together tightly in an ordered array. There's also mobile electrons absorb heat, collide with other electrons, transfer energy, which equals thermal conductivity. Delocalized electrons move freely through the metal structure equals electrical conductivity. The shininess of a metal, that can be related to the mobile electrons reflecting light. And then obviously the last thing, malleability and ductility, which is the non-directional bonding where particles can move without bonds breaking. So they're all the concepts on that sort of submicroscopic perspective, which brings us to our third point, which is the symbolic. So here we would sort of want to do the metal structure representations. As you can see here, we've got four. There are many, but I'll just sort of show you four. And things that you should touch on, obviously, with your students is that all these representations explain many physical properties of metals, but it doesn't explain a wide range of things. So in some cases, densities, melting points, conductivities, and malleability. Now moving on to the second scientific concept, from a macroscopic or real world sort of what we can see level, the ionic liquid coating application is beneficial to the research. So we can sort of say that looking from the real world, the liquid coating is biocompatible, it reduces corrosion, and that ionic bonding, sort of we're looking at the same bonding as table salt, and we can relate it to the periodic table, something that students can see. The left and the right hand sides of the periodic table are interacting to form new substances. If we go sort of one step deeper, the submicro, we're looking at probably ionic bonding. So some things to cover would include outer shell electrons or valence electrons, the stability of having 8 valence electrons. We can delve into metals having low valence electrons that they like to lose, and non-metals having high valence electrons which they like to obviously accept more. The ionic bond in general, metal valence electrons are donated to the non-metal. We can go into cations, we can go into anions, salts that are electrically neutral cations and anions, and ionic liquid coating can be sort of compared as a more complex version of table salt, something that sort of, I suppose, the students can grasp. The salt being neutral is less reactive than the metal, who wants to lose a valence electron. This sort of relates back to the initial macroscopic, something they can sort of see happening. And then we move on to the symbolic, the ionic bonding representations. We have 4 here. So there's so many representations you can use, as long as you sort of share the limitations of each representation. Which brings us to our third concept. It's a bit of a smaller concept, but it can still be touched on, that corrosion occurs at the surface. That's the macroscopic perspective. You know, the surface is a boundary between one substance and another, so the interface when interaction occurs. And, you know, surface particle behaviour affects a substance's physical properties and applications. I suppose it focuses research, determines a testing selection of this research. So that can sort of be touched on the macro level. On the sub-micro level, with surface bonding, you can sort of go into things like the bulk of the substance, ions completely surrounded by other ions, whereas at the surface, you've got incompletely bonded particles, so there's the ability to bond to other substances. The properties of a surface can be explained by bonding at the surface, and then we go into adsorption, or colliding particles sticking to the surface, attraction between colliding particles and surfaces, I suppose as an adhesive force, and compare that to a cohesive force, which is the bulk attraction forces. Moving on to the symbolic, you've got just a couple here of surface bonding representations, which you can go into in a deeper sort of manner. Further ideas to introduce or unpack with students is Unit 2, Area of Study 1. You can do corrosion result, redox reactions, acids and bases, or Unit 3, Area of Study 1, spectroscopic techniques. That concludes the presentation. I'll just leave you with this last slide of the scientific vocab that has been explained throughout the presentation, just to show you sort of the type of glossary terms that the students will be learning. Thank you very much.